Good morning. My name is Artish Rathod from Department of CSE AIML Section C. Today my course title is Matrices and Calculus and topic title is Eigen Values and Eigen Vectors Computations on Virtex-5 FPGA platform cyclic Jacobi's algorithm using systolic array architecture. This is my topic title, and this is on second slide. I mentioned the topic title, which is Eigenvalues and Eigenvectors Computations on Virtex-5 FPGA platform using the cyclic Jacobi's algorithm using systolic array architecture. And coming to its introduction on the third slide, we can see here the introduction about the eigenvalues and eigenvectors. Here we can see the chipboard of the Vertex 5 FPGA. You can see in the image. And coming to its introduction, eigenvalues and eigenvectors are fundamental in matrix analysis and numerous scientific applications. They provide insights into matrix properties such as stability and spectral decomposition, efficient composition of these values in virtual for high performance computing skills. This provide has high performance computing task. Okay, and coming to our fourth slide, the importance of the eigen values computations. We are going to in fourth slide we are going to discuss about the importance of eigen values computations. Eigen values are used in various fields including physics, engineering, and data science. They enable dimensionality reduction techniques like principal component analysis. Fast and accurate eigenvalues algorithms are critical for real-time signal processing. And coming to our fifth slide, here we can see the overview of Virtex-5 FPGA platform. In the motherboard, we can see the Virtex-5 FPGA platform where it is placed, how it looks like in the motherboard, and this is the overview of the Virtex-5 FPGA platform. And coming to its details, the Virtex-5 FPGA offers high computational power. It offers us high computational powers, recognizability for complex algorithms. It easily recognize the high complex algorithms. FPGA based solutions can accurate eigen values computation significantly. Okay, and its architecture supports parallel processing. Okay, its architecture supports us parallel processing, which is ideal for iterative algorithms like Jacobi's method. By Jacobi's method, it supports has a parallel processing. And coming to its sixth slide, we can say the cyclic Jacobi's algorithm fundamentals. In this slide, we are going to discuss about fundamentals of cyclic Jacobi's algorithm. And here we can see the equation of Jacobi's method, finding the eigenvalues and eigenvectors using the Jacobi's method. And coming to its fundamental details, and cyclic Jacobi's algorithm illiterately applies plane rotations to diagonalize symmetric matrices. Okay, in this cyclic Jacobi's we use in symmetric matrix, as we see in the image, which is a 3 by 3 matrix. It symmetrically targets off diagonal elements to zero out. Okay, it's targets the off diagonal elements to remove the zero. Okay, and the algorithm converges the eigenvalues on the diagonal with corresponding eigenvectors. Okay, we are let's move on the seventh slide. In this seventh slide, we see the advantage of using systolic architecture. We are going to see the advantage of systolic architecture using Jacobi's method, and here you can see the question in the image. And coming to its advantage of systolic architecture, systolic arrays facilitate high throughput and parallel data processing. Systolic array which facilitates the high outputs. Okay, and they are well suited for implementing iterative algorithms like Jacobi's method. Systolic architecture are well suited for Jacobi's method. The regular structure simplifies hardware design and scalability on FPGA platform. This is the advantages of the using of systolic architectures. And coming to our eighth slide, implementing Jacobi's algorithm and on FPGA. We are going to implement the Jacobi's algorithm on FPGA. Okay, this is the, you can see the Virtex-5 product overview, and uh, we are going to implement the Jacobi's algorithm on it. The algorithm the algorithm is mapped onto systolic arrays to perform multiple rotational simultaneously. This algorithm is mapped on the systolic arrays, which performs multiple rotations simultaneously. And data flow is optimized to minimize latency and maximize throughput. Hardware modules handle tasks such as rotation, computation, and matrix updates efficiently. And coming to its ninth slide, where we see the design challenges. Here we can see the in image we can see the design challenges, which are containing so many challenges. We can see here how the data are going from one complex to another complex, and how they are going to work. And coming to its design challenges, management is critical for numerical stability in fixed point FPGA implementation. Simultaneization between processing elements must be carefully designed. It is designed carefully. Resources utilization impacts the complexity and scalability of the design. Here, coming to its system architecture overview. Coming to its overview, we have seen this overview in our first slide, and you can see again it's a system architecture overview. And later on, we are going to see the another overview of it. The architecture composes modules for data inputs, systolic processing and output. Parallel processing elements perform rotation calculation concurrently. Control logic architectures for a sequence of rotations and convergence checks. Coming to our 11th slide, data reception and fixed point arithmetic. Coming to a detailed fixed point representation reduces hardware complexity compared to floating point. Scaling strategies ensure numerical stability during composition. Trade-off between previous and precision and resource using uses are carefully balanced. In this trade-off between precision and resource uses are carefully balanced in this, which is a data representation, where we where it has fixed point arithmetic. And coming to our 12th slide, hardware modules and their functions. We can see the hardware module functions in the image. And coming to its digital rotation computation modules calculate given rotations for matrix elements. Data rotating modules facilitates efficient communication between systolic cell. Convergence detection modules monitor of diagonal elements of determined composition. Performance matrix and elevation. This historic FPGA implements architecture high performance, thoughtful, and low latency. Resources utilization includes a logic slice, DSP block, and memory blocks. Accuracy invalidated against software-based eigenvalue computations to ensure correctness. And coming to our fourth slide, comparison with software implementations. Okay, FPGA based systolic implementation out, outper, outperforms CPU and GPU and counterputs in speed. It uses CPU and GPU in speed and power efficient in significantly higher in FPGA solutions. Hardware accelerate enables real-time processing for large matrices. And coming to its application and use cases, Eigen Values computations on FPGA accelerate benefits signal processing and control system. It is applicable in real-time systems like adaptive filtering and beam forming. Scientific simultaneous and machine learning also leverages rapid eigen decomposition. Okay, and this is the applications and use case. Coming to its future directions and enhancement. And here we can see the latest chipset of the Virtex-5 FPGA and future direction and enhancement we are going to discuss, which is incorporating double precision support for higher accuracy, extending the architecture to handle non-symmetric matrices, integrating with higher level systems for seamless development in embars- embedded solution. Okay, and coming to our sixth slide, which is a conclusion and summary of the Vertex 5 FPGA. We are going to our conclusion and the overall summary about this, and we can see the upgraded chipset in the image. And coming to its conclusion and summary, FPGA based systolic implementations of cyclic Jacobi's algorithm offers high performance. It offers us high performance. They enable efficient eigenvalues and eigenvectors computations for demanding applications. Okay, and coming to its continued research will enhance precision, scalability, and integration capabilities. This is the our conclusion and summary on the Vertex 5 FPGA. And thank you for this giving me opportunity. Thank you.